Building construction is the systematic execution of planning, architectural, and design work. It is the process of translating technical drawings into a permanent physical structure. To succeed, an engineer must solve a continuous problem of scale, bridging massive environmental forces with microscopic chemical reactions. Before a structure can rise, the builder must first master the macro environment, analyzing exactly where and how the building sits on the earth. Then they must master the microenvironment, the strict physical and chemical properties of the materials holding it together. We are going to track this process from start to finish. We will select a site, map its physical threats, and formulate a custom concrete mixture designed to survive it. A finished building standing against the elements is the result of hundreds of hidden, interconnected calculations. Site selection is a highly project-specific job. Every decision optimizes for two non-negotiable targets: safety and economy. Engineers analyze the terrain to immediately rule out specific hazardous zones, avoiding waterlogged ground, unstable backfilled sites, and riverbanks. Once a safe footprint is found, the building's orientation aligns to endure external vectors, positioned to manage the sun's path, wind direction, and local rain. These environmental forces dictate the design of the two primary components of any building, the substructure and the superstructure. The substructure's sole role is to safely transfer the entire load of the building deep into the subsoil conditions. The superstructure sits above, carrying out the building's actual purpose, whether residential or industrial, while enduring the continuous climatic conditions. Long before any architectural aesthetic is applied, the local terrain strictly dictates the building's geometry and foundation. To survive those mapped environmental forces, engineers must mathematically quantify how a raw material will behave under intense stress. They calculate its specific weight, the force per unit volume, measured in newtons per cubic meter, and its specific gravity, the material's density ratio compared to water. This diagram shows the concept of the void ratio. It measures exactly how much empty space exists within a material, comparing the volume of voids, air and water, against the volume of solid particles. Beyond static weight and density, materials must be evaluated for their characteristic behavior when actively pulled or compressed by the environment. Engineers contrast ductility, how a material stretches, against malleability. Malleability specifically measures a material's capacity to deform or flatten under compressive stress without breaking or cracking. Structural failure occurs when the specific gravity and void ratio of a chosen material cannot mathematically withstand the macro stresses mapped onto the site. Concrete is a composite material formulated to solve these structural equations, relying on construction aggregate for its physical bulk. This aggregate is sourced from mined particulate matter, separated into distinct supplies of sand, gravel, and crushed stone. These massive piles illustrate the sheer volume required. Those raw mined materials account for a massive 65 to 80% of concrete's total volume. The aggregates are strictly categorized by size, ranging from fine sand to coarse grit, and by shape, graded as round, irregular, angular, or flaky. The selection follows a strict sizing rule. The maximum size of the coarse aggregate is limited by the internal skeleton of the building. It must easily pass through the narrow spacing between vertical steel reinforcement bars. This creates a physical constraint. The internal skeleton of steel reinforcement dictates the maximum aggregate size. Without this precise fit, the concrete cannot pack densely enough to achieve its intended load-bearing strength. But aggregate is essentially inert rock. It requires a powerful chemical binder to lock it into a structural solid. Historically, builders achieved this by calcining limestone to produce caustic quicklime, calcium oxide, which reacts with water to become slaked lime. Modern construction demands more specialized chemistry, relying almost entirely on Portland cement. This flowchart details the matrix engineers use to match Portland cement types, I through V, directly to local site threats. Type I is for general construction. However, types 2 and V provide sulfate resistance, an absolute requirement if the substructure is exposed to toxic groundwaters. Other applications require different thermal and physical properties. Type 3 is ground finer for high early strength and rapid deployment, while Type 4 is formulated for a low heat of hydration. That low heat property is vital. In massive, continuous structural pores like this gravity dam, high internal temperatures from the chemical reaction would cause the solid concrete to crack. Cement selection is a deliberate chemical countermeasure to the geographical threats of the site. Even a mathematically perfect chemical formulation is vulnerable to human execution in the field. The primary catalyst added to the dry mix must meet a strict rule. Water fit for drinking is fit for concrete. It must be entirely free from dissolved salts. The goal is workability, ensuring ease of placement while retaining the concrete's perfect internal homogeneity. Optimal workability requires a highly specific combination of well-graded aggregates and a sufficient amount of fine particles. In practice, sand naturally smoothed in riverbeds yields far more workable concrete than jagged sand manufactured by crushing stone. Structural integrity ultimately relies on engineering a material pliable enough for human hands to mold without compromising its molecular strength. The entire discipline is a continuous engineering feedback loop, where macroscopic geographical constraints strictly dictate microscopic chemical solutions. A high-sulfate soil condition forces the specific selection of Type V Portland cement. Dense steel reinforcements inside the superstructure strictly limit the maximum diameter of the coarse aggregate, and complex on-site formwork demands the use of river sand to guarantee workability during the pour. When all of these distinct variables are successfully compounded together, the finished structure holds firm against severe weather and intense environmental stress. Building construction is the systematic calibration of physical properties to meet the demands of the local environment.